This is Professor Geisler at Cosumnes River College, and this is your short video lecture for Chapter 7, Network Connectivity, and more specifically, Section 7.1, IP Addressing for CISN 301 using the TestOut Client Pro version 8.0 curriculum. Well, what they say here in one skill item is actually a whole lot more. So here are some of the key terms we'll talk about in just a second, how we can go through all these. And in fact, that's just part of the key terms. There is another. So this is a somewhat oomphy chapter, okay, or module, I should say. But it's an important chapter. And in fact, it's so important that you're going to get these kinds of lectures in most any networking class that you're going to take as part of a typical IT program. Okay. IP addressing and subnetting is not an easy topic, but it's actually relatively straightforward. And there's lots of tools out there to help you. Okay. So when we're dealing with things like subnet masks and public versus private IP, there's lots of resources. There's lots of ways of doing it. There's some wonderful downloadable IP calculators, IP subnet calculators, as they're called, both downloadable for your phone and frankly, there's some that you can download to your computer, and there's even some that are web-based. So there's help when it comes to the actual figuring out of the numbers. But in order for you to be able to do that, you need to understand the foundational concepts, and that's what I'm going to focus on here in what will hopefully be a relatively short video lecture. But if it runs a little bit longer than the usual, bear with me. All right, let's take some of these terms. First, what's an octet? Well, an octet is an 8-bit binary number. Okay, and when you take a look at an IP address such as 192.168.1.1, there are 4 octets separated by the 3 dots. Okay, and each octet is a number from 0 to 255, which is 256 total possibilities, right? We start counting with 0 and we go to 255. Like we do on computers, we start counting with 0. And 256 is 2 to the 8th. So what that tells you, since we're using an 8-bit binary number, that with 8 bits, you can create 2 to the 8th different combinations. Okay? So, and it's combinations of, since we're dealing with 8 bits of zeros and ones, and we'll get to how the binary number system works a little bit later on, but much more in the chapter itself. Okay, so here is an introduction again to that concept of octets and 4 octets, and of course each octet again has 8 zeros or ones or a combination thereof. Now, that's what IPv4 addresses are made up of, and we still use a lot of those, even though IP version 6 has been around for quite some time, which doesn't look like an IPv4 address at all. Okay, in fact, it's not a binary, but a hexadecimal address. More about that later. And of course, hexadecimal, if you've dealt with it previously, you know it's the numbers 0 through 9 and the letters A through F. Okay. Because we ran out of numbers after 9, so we had to come up with something else, and the letters, made sense. So hexadecimal, of course, is rather than binary by 2, which is 0 and 1. Hexadecimal means hexa is 6 and deca is 10, so it's 16. So 0 through 9 and A through F is 16 different quote-unquote numbers. And yes, for the purposes of this, we have to find A through F as numbers. A representing 10, B representing 11, and so on, F representing 15, right? Because there too, we start counting with 0. So for a hexadecimal system, we start counting with 0 and we go up to 16. Okay, I'll take that back. 15, 16 different combinations. Okay, 16 different numbers, 0 through 15. All right, we'll get there. A subnet mask is also a 32-bit number, just like the combination of 4 octets up above give you 32. But a subnet mask defines by where the ones are and where the zeros are, which part of an address is part of the network and which part is unique to the client. Okay, so if you have a subnet mask of, for example, 255.255.255.0, that means that the first 24, 3 times 8, right, the first 3 octets, the first 24 bits are ones, because 1111, the 8 ones is the highest number possible in a binary 8-bit environment, so 255. So if you have a subnet mask of 255.255.255.0, that means that the first 24 bits of that subnet mask define the network portion of that address, and the last 8 bits, the remaining 8 bits, define the unique client address, okay, or the host address as it's called in TCP/IP terminology. We'll get back to that. We have public IP addresses, which is any IP address that is used to access the internet, but we also have private IP addresses, which are used for internal networks because they are not routable, okay? And therefore, they can't go out onto the internet. Examples of non-routable private addresses would be 192.168. Okay, anything that starts with that is a Class C private IP address, or a 10 dot address. Any IP address that starts with 10 dot is also not routable. And the 10 dot would be for a Class A address. More about that later. A PIPA, or automatic private IP addressing, has been around for probably about 15 years or so, maybe 20 years. And that is a way for, if somebody happens not to know how to do IP configuration in a small network, for computers, if they cannot develop an IP address for an interface, the Windows world, meaning Microsoft's operating systems, will come up with an address that starts with 169.254. Okay, and the last 2 octets are randomly generated, and there's a process in place to avoid duplication. But basically, this will allow devices on the same network to still communicate with each other, but only in a way that they can handle themselves on their own private network. And again, that's when a manual configuration hasn't happened, or they cannot get an address from a dynamic host configuration protocol or DHCP server that may be unavailable. So a PIPA is an emergency fix. And I say it's networking for people who don't know what they're doing. Hopefully after this module, you won't be among them. A loopback address allows testing of an adapter. And for example, 127.0.0.1, if you ping that address, you are testing your own interface. Okay, so if you cannot ping your loopback address, then once again, there's something wrong with your network adapter. And that's kind of, knocking on your side of the door, if you will, out into the network. A broadcast address is a one address that sends a message to all devices on the network. Okay. And as I say, that's the last valid IP address on the network. So they oftentimes end with 255, but they don't have to. Okay. And there's an address for the network. That's the one that typically ends with a .0, but it doesn't have to. More about that later as we get into more details. And then the broadcast address, yeah, goes to all clients. So every computer is the destination on that network is a destination of a broadcast address. A network address is the front part of the IP address that defines the network or the subnet or subnetwork. Okay. Um, and if you have multiple subnetworks, you have to route between those subnetworks. Now, with the rise of switches, we've we, we've done less routing, we've done more switching. Frankly, because switching uses the MAC address or media access control layer address, layer 2, to determine where the message is destined, where the uh, network segment at that point in time is supposed to go. We don't call it a packet until we have an IP address on it. So switching is faster, but we still have to have the ability to route to connect between, say, your internet service provider's network and your own internal local area network. And in fact, if we have a security infrastructure set up, such as one between the internet and your network, say something called a DMZ, where you've got resources that can be accessible from both the internet and from your internal network, in order for us to efficiently use firewall technology, which sits on routers, we need to route, which means we have to have separate subnets. Okay. There's a bit of a science to create those subnets and how to do that. And I certainly wouldn't expect you to be able to do any kind of network or subnet planning after going through this module, but at least you'll understand what different subnets are and how they're built and how the combination of a network address and a subnet mask, again, defines what is part of the network address and what is part of the host or client address. In most cases, subnet masks are fixed length, which means that each subnet has the same number of addresses, but we can also use what's called VLSM or variable length subnet masks. And you can have multiple subnets with different sizes. For example, if you have a subnet for your servers, you may only have a need for so many servers and the adjoining routers within a subnet. So that could be a smaller subnet. Okay, um, and you can set it up that way with using potentially different subnet masks. Though a lot of businesses would probably say that that's not a good idea because you're never quite sure which one, but you may have to go that route if you say trying to merge two separate networks of one company that bought the other, for example. So you may encounter it here and there. You may use something called CIDR, which is called classless interdomain routing, and you can again allocate, like it says here, IP addresses uh, for certain traffic across subnets or within, and there's a certain notation that goes with it. So instead of having say an address and a subnet mask, you might see an IP address and it's like a /24. Okay, and that /24 is the same as saying I'm using the subnet mask of 255.255.255.0 with 24 bits for the network portion. Okay, so you'll see that notation here and there as well. To figure out whether or not two IP addresses are on the same network, you use a process called ANDing, which is kind of like adding, but not quite. And then you also have the ability to combine two or more networks with a process called supernetting, where you change the subnet mask to accomplish that. So I know this is probably not an easy one just from the terminology perspective if you have never dealt with IP subnets, but not to worry, we'll get there, and we'll do so here rather quickly. So I've mentioned a couple of the different numbering systems already, and the one that you've dealt with, chances are all your life, is the decimal number system, right? And we have got numbers from 0 through 9, and most of us count from 1 to 10, but again, these are computers. They start counting with 0. And the reason that we have 10 different numbers, or that we call base 10, is chances are that most of us have 10 fingers, so that number was a natural, okay, I think for a lot of people, for most people, really. Okay, so we've got symbols representing a value from 0 through 9, and that's the decimal number system. That's, what we use for, our currency, right? That's how we use really for most anything. And we have different positions. So if you take a look at these different numbers, so we start over here with the last number, which is 9, and so that's 10, and the last position right here is the lowest position. We start with 10 to the 0. Okay, so 10 to the 0, anything to the 0 is 1, so 9 times 1 is 9. Then the second position right here from the end, which will be the tens, right? So 10 to the 1, so 8 times 10 to the 1 is 80. Okay, that makes sense for the second position. And if this is singles, this is tens, then the 7 must be hundreds. And you're absolutely right. So 7 times 10 to the 2. Notice we started counting with 0, 1, 2, 3. Okay, and 10 to the 2 is in fact 100. So 7 times 100 is 700. That means that the 6, 10 to the 3 must be 6,000. That's, 10 to the 3 is in fact 1,000. So 6,000. So this number is 6,789. And that's how it works with the decimal numbering system. Now, binary numbers look more complicated, but they're actually simpler because you don't have 10 different numbers to work with. All you have is 2 numbers, the number 1 and the number 0. That's it. You've got 2 possibilities. That's why it's called a base 2 system. And we also we don't know. No, I don't like the last statement. The ones and the zeros aren't known as bits. The bit is the placeholder, and it can either be a 1 or it can be a 0. Okay? And basically, the way this works is rather than, count from, 0, 1, 2, we don't have a 2. We only have a 0 and a 1. So what we have to do after we go from 0 to 1, we have to add a position. Okay? And so we add this position right here, and that looks like a 10, but we call it a 1, 0, and that's the equivalent of 2. And then 1, 1 is the equivalent of 3, okay, because we add 2 plus 1. What do you mean 2? Well, remember in the decimal system, the second position here from the back was the tens. Okay, now the first position hasn't changed. That's still our ones, if you will. Okay, but the second has the tens. Well, we don't have tens, right? Because in the binary system, as I said, we only go, we have 2 options, 0 and 1. So 0, 0 is still 0. And if this is the 1 position, then 0, 1 is 1. And if this right here then is the 2 to the 1 position, that's 2. And then this one would be 2 plus 1, and that would be 3. Why 3? Because when we have 2 bits, we have 2 to the 2 to the second possibilities, and that gives us 4. Okay, so 4 possibilities, 1, 2, 3, 4, starting to count with 0, 0, 1, 2, 3. Moving on then, if we have 3 bits, now we can use 3 positions. Okay, and the leading 0 is like with anything else, not counted. And by the way, did they make a mistake here? And yes, they did. They switched around the 1, 0, 0 and the 0, 1, 1. Let's silly them. Okay. So these should actually be switched around right here. So it should read first after, so 0, 0, 0, that's 0. 0, 0, 1 is 1. 0, 1, 0 is 2. Okay, notice that it matches the last 2 digits of these right here. And then the next one shouldn't be 1, 0, 0. The next one should be 0, 1, 1. Right? So, and then 1, 0, 0. So this first position is worth 1, this one's 2, and this one is 4. Not 3, but 4, because it's the first position is the zeros, and then 2 to the 1, and then 2 squared. Okay, so this number 100 is actually the number 4, which makes sense because it follows after 3. And again, switch these two around. And then 101 will be 5, 110 will be 6, 111 will be 7. And that's the highest number that you can do with 3 bits. Okay. And then you add another position, and that will give you 1, 0, 0, 0. And that one will be the number 8, which is 2 to the third power. So 2 to the 0, 2 to the 1, 2 to the 2, 2 to the third. So that would be adding that position. So following that now, as I mentioned earlier, with 8 bits, you've got 256 possibilities, all the way from 0, 0, 0, 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1, 1, 1, 1, which is 255. But you said, no, 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 no. 256 possibilities, different possibilities. Starting with 0, the highest is 255. By the way, one other way to remember that, if it's got a 1 at the end, a binary number, you know it's an odd number, right? 256 is an even number. Okay, so it's 1 less than that. It's 255 because we start counting with 0. That's binary numbers. And then we also have, as I mentioned, the hexadecimal number. So hex for 6 and deca, Latin for 10. And it's a base 16, not I6. Okay, so this is the number, should be the number 1, a base 16 operating system. I'm sorry, number system, where we count from 0 through F. Okay, and these should all be the same size. These aren't special numbers, but again, A equals 10 all the way through F equals 15. So in this case, FF, the first position meaning 16, and the second position being the 1, right? So 1 and then 16 since it's hexadecimal. So F is 15, and this will be 16 times 15. So 16 times 15 is 240, plus 15 is 255. 255. Okay, 1111, 1111. And notice if I split up these 8 bits, I get 2 nibbles. It's 1 byte, right? Or 2 nibbles, as we call them. And so each one of these independently, if you looked at it that way, this would be an F and this would be an F. Why an F? Because F is the 15th number, as I can see right here. Where do you see hexadecimal notation? You don't see it in IP addresses on IPv4, but you see it with IPv6. So IP version 6 has hexadecimal notation. You also see it with MAC addresses, media access control, for network interface adapters. Okay, so the unique ID that's burned into a network card is has hexadecimal notation. So we have 6 pairs, hexadecimal pairs. That's why if you take a look at a MAC address on a network card, it's, it has numbers from 0 through 9 and letters from A through F. If you see one with a letter G or higher, then you're looking at something different. Okay, you're not looking at something that's in hexadecimal notation. So how do you convert from one to the other? Well, I always tell students, write down these numbers here at the bottom, 1, 2, 4, 8, which are powers of 2, right? From 2 to the 0, which is 1, all the way to 2 to the 7th, which is 128. So these numbers right here, write those down. Okay. And then that's your start of your conversion. Write down those numbers. And then if you have a binary number, then wherever there is a 1, and I wish they'd done this differently or at the bottom, but wherever there's a 1, you add the corresponding number, in this case, the 128. And wherever there's a 0, you add 0. You add nothing. Okay. So since we have, so the 1 for the 128, we don't add 64. We do add 32 right here because there's a 1. We do add 16 because there's a 1. We do add 8 because there's a 1. We don't add 4 because there's a 0. We don't add 2. Okay. And we add 1 more. So 128 plus 32 plus 16 plus 8 plus 1. And that means that 125 decimal is the equivalent of 1011, 1001 binary. Remember, 8 bits can't ever be larger than 255. And of course, it can't ever be less than 0, obviously, as well. Okay. Um, and yeah, if you understand this technique, it's pretty straightforward, though, again, there's IP address calculators that you can download either to your phone as an app or or use them online. Quite a few different conversion tools. Just search for IP subnet calculator, and it'll do a lot of this converting for you. Now, you may also have a conversion the other way, right? Where you're going from decimal to binary rather than from binary to decimal. Well, let's start here with 196. Okay. And the way that you would do this is, all right, you start at the top, again, the left-hand side. Does 128 fit into 196? Yes, it does. Okay. One time. If it's ever more than one, then you need to start one further over. Okay. And you're going to end up with 68. Okay, that's your remainder. And then you go, okay, does 64, which is the next number, fit into 68? And yes, it does. Okay, one time, you've got a remainder of 4. Does 32 fit into 4? Nope. Does 16 fit into 4? No. Does 8 fit into 4? No. Does 4 fit into 4? Yes. One time. Here's my 1. And then I've got nothing left, so I can put zeros for the last 2 bits right here for a conversion, again, from decimal to binary. By the way, the Windows calculator that's built into Windows, and I'm pretty sure the one on the Macintosh as well, if you go to the programming version of that, okay, via the top pancake stack on the top left, you can actually do a conversion for both binary and hexadecimal, and they do octal as well. Octal would be the base 8. Okay, you don't see that one too often around programming, but you do see the binary and you do see the hexadecimal in addition to the decimal. So can you then convert from binary to hexadecimal? Yeah, you're not going to do that too often, but yes, you could. Okay, remember that 4 bits binary equal 1 hexadecimal nibble. Okay, so yes, you just treat each of these individually, and you can go back and forth relatively easily. Okay, so in this case, you've got a 11010011. Okay, so this is the 1101 portion right here. Okay, so 1101, 8 plus 4, we're not counting the 2, plus 1 is 13. And the 13th letter, if you will, the 13th number is D. Okay, and then for the second half, for the 0011, we've translated that up here, and we don't have an 8, we don't have a 4, but we do have a 2, we do have a 1, we add those 2. Here's my 3. So 1101, 0011 hexadecimal is, I'm sorry, in binary is D3 hexadecimal. Okay, so 1101, 0011 binary is D3 in hexadecimal. Okay, and here's that 13 for hexadecimal to binary. Okay, so again, processes that you wouldn't do very often, but that you can do here and there. And I'm just not going to spend a whole lot more time going through this process right here. But use a calculator to help you out. You're not going to have to do this in your head a whole lot. And I need you to understand the different numbering systems and how they're used. We're going to talk more about the applications as to how they're used within networks. So why IP addresses? Well, IP addresses are used for clients, for hosts to communicate across networks. Okay, we have names like servername.domain.edu, like www.losrios.edu, or we can even have a subdomain, right? www.crc.losrios.edu, where CRC is the subdomain. But at the end of the day, computers, since they compute well, deal much better with numerical addresses than they deal with names. Humans tend to be better with names. Okay, but since computers are doing the communicating, why not stoop to their level, if you will, and allow them to do that efficiently? So let's talk about what an IPv4 version 4 address looks like. And by the way, you might be asking, well, if there's a version 6, why are we still using 4? Very good question. Um, it's easier for most people, and there's a lot of legacy out on the internet. And many networks these days do both. They communicate at version 4 and version 6. And in some networks, you've slowly started seeing the version 4 going away, but there's many legacy reasons for keeping IPv4. So again, here's this address format, and this is a private address, isn't it? 192.168. We learned about those a little bit ago. Okay, could have also been a 10 dot, right, for a private address, but this is a Class C private address. So we know this is inside somebody's network. This is a non-routable address. If a computer in this network with that address wanted to communicate with the outside world, then we would have to perform some kind of a routing function in order for that to happen. More about that later. Okay. Now, again, these are octets. What's represented here is only one of those octets. Okay. So let's do a quick conversion. 128, not counting 64. 32 is 160, not counting 16, 8. So this is 168. Okay, so that's the second octet right here. Okay. Again, keeping in mind 2 to the 8th is 256, which means we have from 0 to 255 as possibilities. This number will never be 256, any one of these individually. Okay, between 0 and 255. So now let's add the concept of the subnet mask. And as I mentioned earlier, we have an address right here, and we have a subnet mask. And again, 255 is 8 ones, right? So 255.255.255.0 is the same as 111111111, 111111111, 1111111, 00000000. Okay, so that's where the ending then comes in here in the not too distant future. But fundamentally, what we're doing here is we're saying that wherever there's a 1 down here, that is the network portion of the address. And whenever there's a 0, that's the client or host ID portion of this IP address. So all computers on this network have, with this subnet mask, okay, have a network address of 192.168.1. And all computers who share that network address, you don't have to route in between. They're on the same subnet. And each computer has a unique number. In this case, this computer would be a .42. No other computer on this subnet can have the same address because we have to have unique numbers for computers. Computers are fundamentally stupid. You can't give them decisions that they don't know how to make, or problems that they don't know how to solve. So we can't have two computers with the same IP address on the same network. Okay, so that's what we also call, when it comes to the CIDR, classless interdomain routing, it's just a /24 notation. So if you put a /24 at the end right here, that's what's meant with these 24 bits of subnet mask. Now, sometimes you can have the same address, but with a different subnet mask. So notice here's our 142, but notice now the subnet mask is 255.255.0.0. All ones, all ones, all zeros, all zeros. So interestingly, are these two computers right here on the same network? And since the network portion of this address matches between these two different blue addresses, the answer is yes. These computers are actually on the same network. But boy, Dr. G, that's a lot of computers on that network. Yes, it is. But that's okay. We can switch these days. We've got switch technology. That works. We can handle that. But that's a whole lot of computers. That's like uh, you know, 2 to the 16th different possibilities because we've got 16 bits. Yeah, you got to subtract a little bit for the routers, but yeah, that's what you have. Okay. And 2 to the 16th is roughly 65,536. So, Dr. G, that's a lot of computers on that one subnet. Can you do that? Yeah, with a good switch fabric, you actually can. Would you do that in an organization? Probably not, but you could. Okay. And what does that look like in a Windows environment? Well, if we don't do this automatically via DHCP, then we can type it in manually. And notice we also have, in addition to our IP address and our subnet mask, a default gateway. Okay. And that default gateway is basically just a fancy term for the router. Okay. Um, and now we need to figure out, well, are these, and the router, of course, your way out onto the internet, or at least out of the subnet, it should be on the same network as you are, right? And in this case, we actually have a bit of an issue because this default gateway is actually not on the same network as this computer with the subnet mask. There would have to be an 8 right here for it to match, and it doesn't. Okay, so we've got an issue here, but we'll solve that problem at another time. Okay. All right. Now, I mentioned IP address classes a little while ago, and there are a total of 5 classes recognized. The numbers that we deal with most of the time are classes A, B, and C. Now, there aren't a whole lot of A addresses. Okay, in fact, we have from 0 through 127. We can't use 127 because that's for loopback addresses. We can't use zeros either. And we don't have the 10 available because that's used for private addressing, as I mentioned earlier. Okay. The default subnet mask, I should have put the word default up here, for a class A address is 255.0.0.0, and you can have up to roughly 16.7 million hosts, 2 to the 24, on that network. You always think there's -2 because you have to have the broadcast address, and which is the highest number, and the network address, which is the lowest number. So it's actually 214, and then at least one has to be for a router. Okay. But sometimes when you see like a -2 somewhere, if you're looking at other resources related to the internet, that's what they're talking about, because you can't use all zeros and you can't use all ones. And sometimes the numbers differ depending on your subnet mask. Um, Class B addresses, we have a whole lot more of those. In fact, we have about the same number as this, so roughly 65,000. And Los Rios, for example, has 165.196. Okay. So in the early days of the internet, when educational institutions dominated the IP address space, at the time, ICANN, the Internet Corporation for Assigned Names and Numbers, was silly enough to give out full Class B addresses to community college districts. Okay. And sometimes even smaller entities. And in retrospect, we're regretting that a little bit because the only addresses that you really need to be valid on the internet are, for web-facing resources or internet-facing resources, such as like web servers and mail servers. So chances are all of Los Rios would probably live with a Class C address. Okay. And that would cover all, campuses, centers, etc. It'd be a stretch, but you probably could make it do with that. But Los Rios has 165.196, and we've been using it, and we've actually started moving away from using it all because it's more secure to not have internet addresses that are accessible. So we're basically blocking what be more than perfectly qualified addresses from being accessed from outside of the network, and frankly from being used by other entities that might benefit from them. If you've ever heard that we're running out of IP addresses, that's the reason. It's partially because we never thought this internet thing would get as big as it has. And so again, we made some ICANN made some good sized mistakes when giving out these IP addresses, these ranges way back when. But we're making do. We're doing okay. Class C, again, small networks, smaller businesses would have gotten those. These days, the likelihood of you, when you go to your internet service provider as an organization, of you getting even, anywhere close to a Class C is relatively low, and they're, difficult to get. So chances are they're going to give you just a few public-facing, fully qualified IP addresses. And you're going to have to, depending on the number of servers, and you're going to have to fit in what you're doing into that. Class D is for multicasting. So if you're sending something to not everybody, not a broadcast, but to different computers along the internet, those will be used, Class D addresses. And then Class E would be for experimental or research. So you don't really see those addresses at all. And if you ever want to figure out how do I remember, these ranges, it's actually pretty straightforward. Um, the Class A, the first bit is a 0. Okay. Class B, the first bit is a 1. Class C, the first 2 bits are a 1. Class D, and there could always be more, but at least the first 2 bits are 1. Class D, at least the first 3 bits are a 1. And Class E, at least the first 4 bits are a 1. So if I add the first 4, 128 plus 64 is 192, plus 32 is 224, plus 16 is 240. Okay, and you just heard these other numbers: 128, 192, 22. So that's how you remember them. And of course, the top of that range is always the one below the next one. Lots of interesting stuff in here. If you like numbers, this IP addressing thing is actually kind of cool, binary or not. And again, and you have, did I say ICANN? I meant IANA. Okay. So the Internet Assigned Numbers Authority is what gives those numbers out, and they do it through your ISP. And that's why these days, because we ran out of these numbers, we now use a lot of these private IP addresses. And as I said, they start with a 10 dot, and you'll either see that or you'll see the 192.168 for smaller networks. But I think, Dr. G, 10 dot addresses, that means I've got like 16.7 million different hosts possible, right? Yep. My home address starts with a 10 dot. Yep. If at your house you wanted to attach 16.7 million different computers to your network, have at it. Chances are you won't have the need. Chances are you won't have the space. But that's okay. Since it's not going to be routed, all you need is one address that will get you to the internet. And for my ISP, which happens to be Comcast, even they give me a 10 dot address on their end. So my network, which is private, goes into their network, which is private, which goes out into the internet. And there is routing in the middle that still makes sure that my traffic can get to other sides of the internet. Okay. And once again, here are these addresses that are the classes, okay, for A through E. And again, we really only use the first 3. And here's the private range for each one of those classes. So the 10 dots, Class B is 172.16 to 172.32. You don't see that much. Okay, you either see 10 dots or you see 192.168. You hardly ever see the Class B possibility, which is, it's a possibility, but yeah, you just don't see it much. Okay. So special addresses, we talked about the PIPA addresses. It's actually 169.254, and that shouldn't be an I, it should be a number 1. Okay, so 169.254 is for a PIPA. We talked about the loopback address, and again, that should be a 1. I don't know why they came up with I's for your for the slides. Also known as the local host, and that's when you ping yourself to test your own IP interface. And then the last IP address in the network oftentimes ends with 255. Okay, it doesn't have to, depending on the subnet mask. And everything sends to all hosts on that network. And then we have the network address, which in most cases end with a 0. And as I said earlier, and that's where the -2 comes in right here, host addresses cannot end in a 0 or a 255. Okay, it just cannot, just can't happen that way. So we talked about IPv4 addresses. Remember, we've got 4 octets, 8 bits each. Subnet masks determine which part of the address is the network address and which one's the host address. Classes A through E, even though we really only work with A through C for practical reasons, D being for multicasts, and E for experimental purposes. And that will be the special IPv4 addresses, in addition to the network addresses, which are, again, typically, but not always, for now, all zeros, and the broadcast addresses, all ones. We talked about APIPA, the 169.254, and then, of course, the private addresses. All right, so now that we talked about addresses, let's start talking about subnets and why. And I briefly mentioned it earlier, the idea of security. So if you have multiple subnets, you can separate the outside network from the inside network. You can have a DMZ with other resources in the middle. And, sometimes it's just not a bad idea to keep traffic separate. Let's, in theory, we could have Cosumnes River College, all courses we just have a big hall and we have all classes in the same hall and we all teach at the same time. But boy, wouldn't that be inconvenient because you would have noise from one classroom going, to other classrooms if there's no walls, right? So that's why we have subnets. We separate network traffic. And in the past, we used to say where we separate collision domains for Ethernet. So before we had Ethernet switches, when we still had hubs, only one computer could talk at a time. There was a practical limit to the number of computers that could be on the same Ethernet network. These days, that practical limit has, for all intents and purposes, been eliminated because with a good switch fabric where only the targeted computer, the destination computer, gets the segments delivered to them, or the packets at the higher level. Now we can have many more computers on the same subnet. Okay, so, but we still subnet because it still makes sense for us to keep certain resources separate. So, and it could be that maybe we want all the folks who share, in the accounting department, to have that be a separate subnet. Or, by department, it's not typically how it would be done these days. It would be more so as to how the computers are used. Like, for example, the computers in room BS 153 on the main CRC campus. That's our networking lab. That is treated completely separately, even from the other computer labs which are right next door, because of the types of things that we do in that room with our computers. And so that's why they call that network crash and burn. So if, as part of instruction, some students decide to create a secondary DHCP server that could potentially, as clients try to renew their IP address, issue those clients addresses that don't work with the rest of the campus network, um, then yeah, we do want to have that network separated in a separate subnet. Okay, and so that's where subnetting still makes sense. So you'd have all your servers in a subnet and all your printers in a subnet. And there's other ways to split things up, many different ways of doing that within networks, but subnets are one good way of again splitting those um, areas of potential, conflict, if you will. And frankly, if there was a computer or with a defective network card that would just keep sending, broadcasts after broadcast, at least that could be limited until that computer is determined and turned off to the subnet on which that computer is located. It wouldn't affect the entire organization. Okay. So how does subnetting actually work? Well, we have subnet masks. And the 192.168 is a private address, class C, we said. And for class C addresses, the default subnet mask is 255.255.255.0. Class C, the third letter, 1, 2, 3 octets. Class B, 2 octets. Class A, just the 1 octet, 255.0.0.0, and that would be the 10 dot addresses. Okay. So, but here we're dealing with a class C, and what if we changed that subnet mask? And what if we didn't change the entire octet, but what if we just added a fraction? So in this case, only 2 of those 8 bits in the last octet. So our subnet mask now looks like this. So what this does is it makes the network portion a little bit longer, okay, and the host portion a little bit shorter. Now, these days we would typically go the other way, so I'm not quite sure why they're using this example, but let's bear with it. Okay. What they're trying to do is they're trying to say, well, if you have a certain subnet mask that by default, you can extend it further to create more subnets within your address. That's why they're doing this. Okay. Um, and so here, so in this case, our subnet mask has now changed from 255.255.255.0 to 255.255.255.192. Okay, Dr. G, where's the 192 coming from? Well, if this first bit is worth 128, remember those 128, 64, 32, those 8 numbers? So write those down again, okay? And so this is, the first number is 128, the second one is 64, that's 192. Ah, because the rest is 0, right? We're not adding anything else. So here's my 192. Okay, so what that means is that if I have, and this isn't entirely true, so I'll have to modify here in just a little bit, and the example they gave is in kind of in a confusing way, so we'll get there. But if I have 2 bits, okay, that gives me 2 to the square different subnets. But this is where instead of using an entire octet at a time, you can use a fractional octet to give yourself more subnets in an address, in this case a class C, that your business may have been assigned. Okay. Now, how many hosts per subnet? Well, in this case, if I have 6 bits, that gives me 2 to the 6 power. Okay, and 2 to the 6 is 64. But remember, I can't use the all zeros and I can't use the all ones. So I only, instead of getting 64, I'm really only getting 62 addresses. Okay, so and here's for these different subnets, the lowest and the highest. Okay, um, so and yeah, okay. So here's the numbers that I can use, starting with 1, and here's my 62. 65 to 126 is 62. 129 to 190 is 62. 193 to 254 is 62. Count the first one, count the last one. Okay. All right. I've briefly mentioned CIDR as well. And so here's that slash notation. So if I have 255.255.255.0, here is my 8 bits plus 8 bits plus 8 bits is 24 bits. So I would write an address such as 192.168.5.0 slash 26, and that's the same as 24.255.255.192. Okay, 192 for these two. So that could also be represented as slash 26. Same 62 usable IPs within my subnet. All right, and number of subnets, 8. I got to subtract the 2. Okay, there as well. All right, subnets part 1. Here's your 16. Okay, so slash 16, which means I'm only using the first 2 octets right here. Okay, and so there's some exercises that you can go through to determine how many subnets you can create with how many bits, and you've got your CIDR notation as well. All right, so let's take a look at other things that you might encounter, which are either a fixed length subnet mask, which means that there's the same mask and number of addresses, or what's called a variable length. And again, that's where your CIDR notation comes in. In most cases, again, in the network, you're going to find consistent numbering unless it's a combination of multiple networks that somebody had to combine because, let's say, one company bought another, or a different site different location has a different setup. But we can do a lot with um, private addresses these days, and ways to get from one location to another to have the same IP address space. So you're not going to see verbal link subnet masks very often these days. But in case you do, you need to know how to get from one to the other. And frankly, as long as your routers and your DHCP servers are properly configured, it's not an issue. It's just a bit of a planning issue that you need to worry about. And I'll let you learn about that, but I'm not going to spend a whole lot more time talking about it here, because the likelihood of you encountering it is relatively low. Now, ending you will encounter, and again, that's how we figure out whether or not a host is on the same on the same network as another. Okay, so if you take a look at an IP address and a subnet mask, wherever there's one in the subnet mask, the ending result goes down here, and that gives you your network ID. So if you have two addresses, they hopefully share that subnet mask. And if you AND both of those and the result of the ANDing is the same for both combinations of IP address and subnet mask, then those two computers are on the same network. Okay. So, and again, this is a /21 address right here. Notice um, everything else down here is zeros, right? Because 21 only goes through the first 21 bits. So 22, 23, and 24, these last 3 bits of the third octet are part of the host, right? But in this case, since we're ANDing, that creates our network address. So in this case, yep, that's that's the other way to look at that. You would use the fixed length in private networks. You can use the VLSM in public networks, but again, it's only supported by advanced routing, not outing, advanced routing protocols. Jiminy Cricket, they made several mistakes here in these slides. Um, so yes, there's a way to combine with what's called supernetting, multiple smaller subnets into one larger subnet. Um, and notice they're sequential, whereas these ones are not. Okay, so they need to be contiguous. Um, but yeah, there's a way to actually use a shorter subnet mask to supernet multiple adjacent addresses. I don't know where they're throwing that in here, but it's more of an advanced concept. But I think they're just trying to give you the kitchen sink here, to at least expose you to some of the terminology that's there. Okay. Um, so much about subnet masks and the ANDing process, which you will need to use regularly. And again, that's where those IP subnet calculators come in real handy. And then the supernetting you may see here and there. But again, we can do so much with private addresses these days. And we can go all the way up to those 10 dots. Again, 16.7 million addresses. That gives us a lot of different possibilities. Even if we create, we use one subnet, one octet, the second octet just for subnets, that still gives us 65,000 addresses in each of those subnets. We can do so much with that. Okay. Now, we've talked about IP addresses, and we've talked about that every computer, every device on the network needs one. But how do we actually get them, those IP addresses? Well, we can manually configure, which is what's called a static IP address. Okay. We would put in an IP address, a subnet mask, a default gateway, which again is the other word for the router to get out of the network. And in order to do name resolution, we would want at least one DNS server address. Typically, you will see 2 DNS servers for redundancy purposes configured. But rather than doing that manually and having to keep track of it all, it's typically much easier to use a process called DHCP, or Dynamic Host Configuration Protocol, where a computer, once it comes online, gets its IP address from a designated server, which has a pool of addresses that it makes available. And then that address is leased to the computer, and the computer regularly renews its lease. to make sure that it can continue to have an IP address. And frankly, it'll try to keep that IP address as consistent as possible, which for a client, it doesn't really matter that it is. And by the way, if there's one type of computer that you want to manually configure so the IP address doesn't change, it would be a server. Let me give you this example. If you wanted to go to your grocery store, okay, if that grocery store moved to different parts of town each week, wouldn't that be confusing? Right? So the server, the grocery store, should really ideally always be in the same place, or meaning in this case, have the same address. If a client, that goes to that store has a different name today than it did last week, that doesn't really matter so much. Okay. So that's why you can have what are called DHCP reservations based upon a server's MAC address. And so you could, in theory, uh, ensure that a server would have the same address via a DHCP reservation. However, in most cases, it's done manually because what happens if that DHCP server for some reason is not available? You'd still want that server to be up and running and to be able to provide resources to remaining computers. So the IP um, addresses for servers are in most cases configured statically, as you would find them for most routers and other network equipment as well. How does the DHCP process work? We have what's called a DORA. So it starts from the bottom, DORA. And there's a packet that's sent from the client to the server and says, a discover, hey, is there somebody out there who can give me an IP address? And the DHCP server will respond and says, hey, how about this IP address? And the client says, thank you very much. Hey, is there anybody else out there with that same IP address? No? Anyone? No? And then the server says, okay, there isn't. Okay, now we can acknowledge, hey, client, here, now you have your address. Go ahead and be part of the network. Go about your business. Okay, so that's the process for DHCP. Of course, a simplified, but fundamentally, that's how that works. And the DHCP server doesn't just send an address to the client. It sends, again, those components that we talked about, an IP address, a subnet mask, the default gateway, and in most cases, domain name server, DNS server information. But it could also be other things like mail server information, time server information. So DHCP will get a client set up on the network. Here's one problem. The DHCP process is a broadcast process, which is limited in most cases, unless somebody foolishly configures a router otherwise, which is really not a good idea. But in most cases, a broadcast stops at the router. Okay, so how do you solve that problem if you have clients on the other side of a router that still need to get an address from the DHCP server? Well, that's not a problem. You can actually configure the router as what they call a DHCP relay agent. And then the router would take that DORA, the first request, and then say, hey, yeah, I know who you're trying to reach. Let me forward it to the DHCP server. And then that relay agent then facilitates the communication between the router, I'm sorry, between the DHCP server and the client that's looking to get connected. Okay. And if you are going to use a Cisco router, this is what the commands would look like. Okay. So you can actually use what's called a helper address. And on a Cisco router, these commands would turn your router into a DHCP relay agent. Again, keeping in mind that this would be the address of the DHCP server right here. And if you didn't know this was for Cisco router, not to worry. I teach some of those classes, so I can recognize it. And if you've taken some of the Cisco classes, hey, you might just recognize that as well. It's typically taught in the second Cisco course, I believe. So yeah, you may have seen this already. Goodness, Dr. G, you said short video lecture. I told you this was going to be a big one. Okay, and it is. But There is a somewhat oomphy lab to configure IP addresses. So do lab 7.1.11. And the format of an IPv4 address, 4 octets, 8 bits each. What's the purpose of a subnet mask? To separate the network address from the host or client address. The address classes for IPv4 are A, B, C, D, and E, where we don't really use D and E. A is 0 through 127, B is 128 through 191, C is 192 to 223. Oh, Dr. G, you remember those numbers? No, I just calculated them because, right, the higher end of the range is always below the next one. Not that difficult to figure out. The purpose of subnetting, to be able to separate domains of potential problems and, frankly, for security reasons as well. And to calculate the number of hosts per subnet, you need to take a look at the remaining bits to the whatever number of bits power. Remember, you've got to subtract the all zeros and the all ones. And the /14 in this address, here's your CIDR notation. That means that the subnet mask would contain 14 bits, which would be 255. That's the first 8. And then we have 6 more. So 128, that's 1, plus 64 is 192, plus 32 is 224, plus 16 is 240, plus 8 is 248, plus 4 is 252. So the subnet mask in this case would be a 14-bit subnet mask and would be 255.252.0.0. And if you didn't figure out this last piece, if that's not in your wheelhouse yet, don't worry. Again, you're going to come across this if you're going to be anywhere around networks many times. And frankly, sometimes I think as professors, we like to teach this because it's kind of cool. It's kind of fun. So I don't want you to be afraid of it. I want you to kind of, get used to it and embrace it. And once you've figured out how this works, it's actually kind of cool. All right. So much for section 7.1. I swear the following sections of this module are going to be shorter, but this was a big one. So make sure you spend the time with the lab. All right. So much for 7.1.